so Gauss's law, what is it for? The short answer is it's to calculate the electric field strength. And notice I emphasize the word electric field strength. That means I'm looking at the magnitude of E. Gauss's law is it's only useful to calculate the electric field strength, which means this is a lazy way of writing this. Okay, so please differentiate this versus this. Okay, so the left-hand side without the vector sign is the electric field strength, which is the magnitude, which is always positive, and this is with a vector, which means it has x and y and potentially a z component. Okay, so at least more than one component usually. All right, so it calculates the electric field strength. Now you might ask, I already know a formula for that, right? E equals to kq over r squared. Now that is only true for point charges. Never use this if it's not a point charge. So you have two questions. If I want to find electric field strength, you need to ask yourself, is it a point charge or is it not a point charge? If it is a point charge, then you're done. You use this formula. If it's not a point charge, you need to use Gauss's law. So the first thing I would advise you to study this is memorize this, commit this to memory. Not that hard. On the left-hand side is EDA, on the right-hand side is 2 over epsilon. And here is something the textbooks don't write. Write down the Gaussian surface you're interested in. So name it S. I'll show you in a quick example how this would work. So let's say I have one charge, which is minus Q, but this time I am surrounded by a thin shell of another charge, which is 2 capital Q, and let's say a third layer of charge. Just trying to make this. Probably you won't get 3 layers, but it doesn't make too much of a difference once I get started of charge like this. So there's 2 thin shells like this. How do we use Gauss's law? The first thing we want to do is draw the electric field lines. Due to the symmetry of the problem, the field lines is going to be spherically symmetrical as well. It's going to radiate out. Which way is it going to point, the arrows? Well, remember, field lines is to use a positive charge to test it. And so in the middle, over here, if I put a positive test charge, which way will it go? It's going to attract from positive to negative like that. So the electric field lines in the middle are going to point this way. How about in this section? In this section, if I put a positive charge here, which way will it go? That's right, it'll go this way. So in here, the electric field line is going to point this way. And finally outside, which way is it going to go? If I put a positive charge here, well, positive charge is going to get attracted to this shell, right? So outside. So the electric field lines tell you how positive charge moves. The first thing you want to solve this is copy this down. So as I mentioned, I will write down the Gaussian surface that I'm interested in. It's always important whenever you write integrals to write down a surface. So the first thing is you want to solve, let's say I'm interested in the electric field strength over here. Okay, how do I do that? Well, if I want the electric field strength over here, I need to draw a Gaussian surface over here. I'm drawing a sphere, a circle, or actually it's a sphere, because of the symmetry of the problem. You want it to intersect the electric field lines in a rather nice way. Okay, so let's solve the right-hand side of it first. So the right-hand side, it's easier. So you can write down, first let's copy exactly how it is. So it's asking for the charge enclosed inside S. So you're going to call this surface S. So the charge inside is minus Q. Okay, that's easy. So now let's look at the left-hand side and then we'll match it together. The first step is to copy exactly the same. So that's always a good habit. Now you have one surface, so that's good. You don't need to break this out. But how do we deal with this integral? So first let's look at dA vector. The dA vector is an area vector. What's an area vector? You pick up, I'm interested in this point, right? So let's zoom in and pick a small area over here, right? The surface area of this, remember it's a sphere. The area vector is always defined as the vector that's perpendicular from the area like this, 90 degrees from the area, pointing out away from the interior. So that's the area vector, okay? So that's dA over here. How about E? E is the electric field. Well, the electric field where? The electric field on S. Okay, so over here, let's zoom in again, on S, or at the point that I'm interested in, which way is the electric field pointing? Notice my arrow. Which way? Inwards. Right, notice the arrows of the electric field lines, right? So E is pointing in here, dA is pointing outwards. So next thing you need to know is dot products. Quick review of dot products. Very simple, A dot B, if they are parallel, it's AB. If A and B is anti-parallel, it's negative AB. if in general, it's AB cosine theta, where theta is the angle, it's the included angle between them. So if it's anti-parallel, right, the angle between them is 180 degrees, cosine 180 degrees is -1. If they're parallel, the angle between them is 0, so cosine 0 is just 1. So over here, we have E dot dA. Look over here, which case is it? Is it a random angle, 90 degrees, 180, or 0 degrees? 180, they're anti-parallel. So this becomes negative EDA. Negative EDA. Now notice there's no vectors on this side. They're all magnitudes, right? So get rid of the scary vectors. Can I pull the E out? Is E a constant? E is not a constant in general, because the further away from the sphere, the weaker E is going to get. However, E is constant on S, right? Because of the symmetry. There's no reason why E is not constant on S. So fortunately, we're integrating over S. So as far as the integral is concerned, E is a constant. Now I just have to integrate dA, which is A. A of what? A of the surface. What's the area of S? Remember, that's a sphere, right? So what's the area of S? 4 pi r squared. So what's r? I need to define this distance. Right? So I'm calculating the electric field at distance r over here. So 4 pi r squared. Good. Now let's match the left-hand side to the right-hand side. So we get minus E 4 pi r squared is minus Q over epsilon. What is our aim? Our aim is to solve the electric field, Q over 4 pi epsilon naught r squared. Notice it's positive, as it should be. Electric field strength is always positive, it's the magnitude. Okay.